This is a model building problem or based on the distance formula. The distance between 2 points x1, y1 and x2, y2 is given by this formula. Square root of x2 minus x1 squared plus y2 minus y1 squared. Now in our case, in part A, we have 2 points 0, minus 1 and x, y. So in our case, the 2 points are P equals x, y and 0, minus 1. So the distance would now be the square root of x2 minus x1 it should be 0 minus x squared plus y2 minus y1 squared, and we end up having square root of x squared plus y plus 1 squared. Now since we want this distance as a function of x, we're going to replace y with the given equation there. So x squared minus 8 plus 1 squared. So the function here for distance is x squared plus x squared minus 7 squared. If we plug in x is equal to 0, d of 0 would be square root of 0 squared plus 0 minus 7 squared, which is square root of 49. You get a distance of 7. And if we plug in x is equal to negative 1, d of negative 1 would be square root of negative 1 squared plus negative 1 squared minus 7 squared, which would be square root of 1 plus 1 minus 7 squared, square root of 1 plus 6 squared, which would give us square root of 37. Now I already have graphed this function. I plugged the distance function here and properly I have x squared plus x squared minus 7 squared, and I close it with a paren for the square root function, and I graphed it, and you can see there are two low values for distance. Distance is on the y-axis, and there are two low values, small values. To find those values, what we can do is press second trace and select number 3 and go to the left and select a left bound, go to the right and select a right bound, hit enter, and you get the minimum. So the minimum happens at x is equal to plus or minus 2.5495. As you can see, it's exactly the mirror image. The right hand side is the mirror image of the left hand side, so the x values would just be the negative of each other, and the smallest distance at the x is simply 2.598, which is nothing but the y value. So this is a simple model building problem that uses the distance formula. This is another model building problem, slightly different. So we have a right angled triangle. It has one vertex on the graph, y equals x cubed. This is the graph, y equals x cubed, and the vertex is xy, and another at the origin, and a third up there. So we would like to express the area of the triangle as a function of x. So area of a right triangle is half times base times height. So the height in this case is that. So the distance between the origin and that vertex, so the height would be y, and the distance along the x-axis, the number of units, that length would be the base, so you'd have x. So these are products. Let's distinguish between the x's and product signs. So we have 1/2 x times y, but our objective here to express the area of the triangle as a function of x, so we have to replace this x, so we can replace, we have to replace that y, and we have to write it in terms of x. It is given in the problem that y is x cubed, so we have 1/2 x times x cubed. So the area would be x raised 4/2. Here we have another model building problem, and so we have a circle of radius r inscribed inside a square, so that's what we have, and the area of the circle is pi r squared. That is something we need, and the area of the square is just a squared, where a is the length of a side, and we should also know the perimeter of the circle. So the perimeter of the circle is 2 pi r, and the perimeter of the square is the sum of all sides. So if the side length is a, then it should just be 4a. So since this is a circle, the radius is the same on all sides, so that length is r, and so is that length. So now we know the length of the side for this particular square is r plus r, so we have 2r. So we would like to represent the area of the square as a function of the radius of the circle. So a is the area of the square, and r is the radius. So we know the area of a square is a squared, and we know the length of the side is 2r based on the figure, so the area would just be 2r squared, so the answer is 4r squared. So the area of the square as a function of radius is 4r squared. Now we'd like to express the perimeter of the square as a function of radius. Let's call perimeter as p, so p of r would just be 4 times the sum of all sides of a square. So the length of each side is 2r, so I'm plugging back in this formula the perimeter of the square, which is 4 times a, so I have 4 times 2r, you'll get 8r. So the radius, the area as a function of radius is 4r squared, and the perimeter as a function of radius is 8r. Keep in mind that this area and the perimeter are for the square and not of the circle. So in this problem we need to know a few things. First, area of an equilateral triangle, which is square root of 3/4a squared. An equilateral triangle is a triangle where all sides have the same length. So in our problem, instead of a, I believe they're using x. So we'll have x, x, and x. So the area can be written as square root of 3 over 4 x squared. So we have this wire that is 10 meters long, and we cut it into two pieces. So one piece will be shaped as an equilateral triangle, the other piece will be shaped as a circle. So an equilateral triangle, if you say the side length is x, there is x plus x plus x. So we have 3x somewhere here, arbitrary, and the remaining would be 10 minus 3x. When you add them together, you get 10 meters. So now we know the side length of the equilateral triangle is x, and the whatever distance that is left, which is 10 minus 3x, must belong to the circle. So if we take the second piece and form a circle, then the circumference the circle would be 2 pi r. Now what we have to make use of this circumference 2 pi r, which would equal 10 minus 3x, because I'm taking this wire and I'm turning it into a circle. Why am I using the circumference? Because we do not know the radius of the circle. So now the radius would simply become 10 minus 3x over 2 pi. Now that I know the area of the circle, the radius of the circle, the area of the circle would be pi times r squared, which would give us pi times 10 minus 3x over 2 pi squared, which is 10 minus 3x squared over 4 pi squared times pi. The pi's will get cancelled. You will have 10 minus 3x squared over 4 pi. So the total area in this problem would be the sum of the area of the square plus the area of the area of the triangle plus the area of the circle. And both of them are in terms of x, the side length of the equilateral triangle. So we will have square root of 3 over 4x squared plus 10 minus 3x squared over 4 pi. Now what is the domain of A? A is an area, so the smallest value x could take is 0. We would like to have a distance, a length in such a way that 10 minus 3x is greater than 0. We want this length to be greater than 0. So if 10 minus 3x is greater than 0, then 10 is greater than 3x. This would mean 3x would be less than 10, which would imply x is less than 10 over 3. So we would require x to be greater than 0, which is the length, and x to be less than 10 over 3. The domain of A of x is between 0 and 10 over 3, and of course we cannot include 0 and 10 over 3, because if you plug in 0, that distance would become 0 and that would become 0, and it would make no sense. And in part C, for what value of x is A the smallest? So we need to graph this. So let's take the area function. We know the domain that we have determined, x could only be between 0 and 10 over 3. And our function here would be square root of 3 divided by 4. I could just write it as square root of 3x squared divided by 4. That would be the area of triangle, and we're going to add the area of the circle, which is 10 minus 3x squared divided by 4. And let's graph this. And we get a nice little curve, and you can see the area is the smallest right over there. So we can easily find that by doing second trace. Number 3, select a left bound, go over, cross the minimum value, and select the right bound and guess. So the minimum value of x in this case will be 2.795, and the area, the smallest area at this value of x is 4.0347. So there were a couple of things in this particular problem in terms of setup. The fundamental concept here is to understand that we start with the side length of an equilateral triangle. Everything has to be expressed in terms of x. So we know, since the side lengths are the same for an equilateral triangle, the total length that is required to form the triangle would be 3x. So the remaining distance or length out of 10 meters would be 10 minus 3x. We're going to make use of 10 minus 3x to find the radius of the circle. And in order to find the radius, we need to make use of the circumference, and the circumference of the circle is 2 pi r, setting the circumference 2 pi r equal to the length, the remaining length that we cut, 10 minus 3x. We end up getting r. We plug in r in the formula for the area of the circle, and we find the area of the circle. Now we have the total enclosed area as the area of the triangle plus the area of the circle. To find the domain, we've got to keep in mind that the value of x has to be greater than 0, and this bit has to be greater than 0 also. If that length has to be greater than 0, then doing a little bit of algebra, you can see x has to be less than 10 over 3. So the domain for the area is between 0 and 10 over 3. In other words, you cannot have an x value greater than 10 over 3 to find this area. You cannot have an x value less than 0 to find the area. Then we plugged in this function in the calculator and found the minimum value of x, where the area is the smallest, and the smallest area is 4.0347. this is a model building problem where we have to inscribe a cylinder in a sphere and express the volume of the cylinder as a function of h, which is the height of the cylinder. So the volume of the cylinder is pi r squared h, and the right angle here is going to play a role in expressing the volume in terms of h. So by looking at this picture, the height of the cylinder is h, which would mean that length right over there, it's h over 2. So this is a right angled triangle, and we know something about a right angled triangle. The Pythagorean theorem. H over 2 squared plus r squared must equal to capital R squared, which is nothing but the square of the hypotenuse. Capital R is the radius of the sphere. So using this particular expression, we could actually replace r squared. R squared would be equal to capital R squared minus h over 2 squared. I moved h over 2 squared from one side to the other. So now the volume of the cylinder is simply pi r squared times h, which would be pi times r squared minus h over 2 squared times h, which is pi times r squared minus h squared over 4 times h. You may ask, well, we wanted this volume to be a function of h. Model volume as a function of h. But then there is this r, and you might say, well, probably we have the wrong answer. Technically, we do not, because if you read the question, the sphere of fixed radius r, which makes this r a constant. So since that is a constant, this expression is simply a function of h. So we have technically modeled the volume of the inscribed cylinder as a function of h.